So for those that are gone, we can go over the notes that we have. A buyer wants to a buyer wants to have 2,000 grams of ammonia. Now that might be a small amount of ammonia. However, it's just fictional, and so the numbers will work. If the Haber process gives a percent yield of 42%, how much hydrogen is required to make that much ammonia? From an excess amount of nitrogen, meaning we do not have to worry about a limiting reactant in this. And normally you would, this would be very realistic. The Haber process is not overly good amount of percent yield on it. It's not all that efficient, and therefore needs to obviously be improved, but it's the best that we have. The fact that we have excess nitrogen is also very realistic in the fact that we have nitrogen in 78% of our Earth's atmosphere, so limiting that would be very odd. What we are going to be limited by would be the amount of hydrogen. Now, it is one of the few reactions that you have to know by name for most chemistry classes. With that, we do have a lot of the information that we need given to us in the fact that we know that we need hydrogen and nitrogen to make ammonia. And again, a lot of it comes down to deciphering what we have and then knowing what's that going to make. Now, when we do this, we need to make sure that we also pay attention to those diatomics, as we have there. Then going through and making sure that we have this whole process also balanced. To help us out. It is a problem that, again, we have done in the past, so the balancing part kind of goes away or isn't as important for us. Like all good stoichiometry problems, we're going to have to find what we need, and so we have, in this case, we will want to have the formula mass for our ammonia. We will also need the formula mass for nitrogen, but because it's diatomic, it should be a lot easier to calculate. And saying 2 times 14.01 should be a lot easier to calculate, so I'm just going to have that written as is. The ammonia, though, that one we're going to have to calculate and move, and I think I'm going to have to move this as well to another spot or farther away so that when I come back in I can do that actual calculation for it. Now when we look at our nitrogen and our hydrogen, 14.01, hydrogen is the 1.01, 14.01, 3.03 to give us 17.04. Okay. Those are the common, like, oh yeah, I always have to calculate those things for that. Now, when it comes to this next step, it's the where do I go with this? Because the 2,000 grams of ammonia, is that my actual or is that my theoretical? And it's hard to distinguish that. If you want to buy something, do you want to buy the theoretical amount or do you want to buy an actual amount? Actually take home a certain amount. So the 2,000 becomes that, how much do I actually want to buy? And so we need to actually figure out and go, okay, that's the actual amount that I want to make. I don't know how much I have to, in theory, potentially make, because that's what we're going to have to look at, is how much hydrogen do I have to actually make 2,000 grams of ammonia. So we're going to have, and the fact that the process is only 42% effective is going to really limit some things for us. And so it's got to have to think about the problem a lot differently. And so we actually have to do a calculation that we haven't really done and utilize our 2,000 of our actual over our theoretical. I'm going to convert my percentage into a decimal place, into a decimal right out of the way to give us 0.42. I need to figure out what my theoretical endpoint is going to be so I can actually add the correct amount of hydrogen. Because if I try to find out how much hydrogen for 2,000, it's going to be like 56% less than what I want. I don't want to come up short. The buyer isn't going to be happy. So we have to come up with that. And what we do is we take our 2,000, divide that by 0.42, and from there to solve for our t, and I just did some algebraic manipulation for myself, and then we can now see from there that my calculation gets me. So after that calculation, I now actually have my new starting point, and that is my 4,761, and I'm just going to go with a 0.9, and that will be grams of ammonia with that as well. Now this is getting really busy, so I'm going to need to do some erasing so that I can get rid of some things for us. And with that, we'll look at and kind of going. And this, now that we have our actual, that becomes an important part of this. Is what do I do with it all? And when I do what I work with is my new values that I've calculated, utilizing all of that, and continue doing a normal stoichiometry problem, because that's what a theoretical calculation is. I need to take the grams of ammonia and make it into our moles of ammonia, utilizing our molar mass, which is normal for us, and we've been doing that. We use our calculated value that we did, the 17.04 grams per mole. Oh, I already did the grams, so I should probably get rid of that. And so now that I have it in moles, because that's what we want to convert to, I need to utilize the fact that I can utilize my mole to mole ratio. Well, it's not 1-to-1. Instead, it's actually 3-to-2, making sure I put things in the right spot. That's why a lot of times I prefer to actually write out my knowns and unknowns, or my wants and givens, and then come back in and fill in the numbers, because I find that I make mistakes if I do it the other way, as I kind of just did. And then from here, we utilize again, and I calculated the wrong thing down here. It was supposed to be hydrogen, and that is equal to 2.02. So nobody called me out on that. Thanks, second hour. And so we have to go with that, and calculating the 2.02 grams of hydrogen and 1 mole of hydrogen, and we should be able to do our calculation now. When we multiply across the top and then multiply across the bottom, I'm going to find and kind of condense this down so that it's a little bit easier for us to see some things. Then go across the bottom, 17.04. That, and then just do the. With that calculation, I end up with a value of, I'll write it in a different color, 313.3 grams of hydrogen with that. It's a little bit different of a percent yield problem. However, it should work out just fine, because that's in theory how much and that unfortunately is actually how much I have to add of hydrogen, because the actual process is only 42% effective, or some might look at it as 57% ineffective, and so you have to account for that when you're adding everything into it. Let's take a look at the next one. Next one has the chemical reaction given to us, and that we have 15 grams of each reactant was mixed, 15 grams of a product was formed. What is the percent yield? Okay, the 15 grams of our product, the C7H12O2, that is an actual value, and so we need to be mindful of that. Okay, and what gets a lot of times, sometimes students, is how this is worded, in that we have 15 grams of each reactant. We only see two numbers there, but in all reality, that's three numbers. So this is one of those kind of like harder stoichiometry problems, in that we have to do a limiting reactant problem before we can even do the regular calculation of everything. What's nice for us is the fact that this is balanced for us, and so we don't have to do a lot of that as well, but we do have to do the limiting reactant. We have to calculate the molar masses for everything as well. I'm probably going to calculate the molar masses for these values off screen, just so that I'll have, because it's a limiting reactant problem and a percent yield, I'm going to need as much screen as I possibly can. So I'm going to calculate them off screen, and so you won't actually see that process taken out, which I don't think at this point you need to actually find anymore. So what I'll do is, again, we're going to calculate out, we need our C3H4O4 calculated. I need to have my C2H6O. That must be a ethanol of some sort, I'm guessing. Might or might not be. And then I also need my product of C7H12O2. And so I'll be calculating these values off screen. So for the first one, I calculated out at 104.03 grams per mole. For this ethanol, I think it's what it is the 46.07. Then we'll go with grams per mole of that. And for this one, we have 128.17 grams per mole. Now I need to do a limiting reactant with my two values that I have. That would again be this, the first two values, with my product being right indicated with the yellow dot. We can now start that limiting reactant problem out. And so the way I like to do them is to start with both one on top, one on the bottom. Which one you start with doesn't really matter. You need to convert both of them into moles. So when we go with that, I'm going to just start and just keep them in the same order, 104.03 and then 46.07 grams, and that would be moles of the C2H6O. And then 1 mole of C3H4O4. I'll need to do my calculation of that, my 15 grams divided by 104.03 to give me a mole of 0.144 moles of C3H4O4. And then I'm going to need to do 15 divided by 46.07 to see that I have 0.32, and I'm going to round that up to 3 significant digits, and so it'll be a 6 moles of C2H6O. Now I need to just figure out which one of these is my limiting reactant. For my class, again, normally we just convert one of them to the other one. Other reference materials will have you converting both of them into each other and then do the comparison. We're not looking at how much excess we need, so that's not a necessary evil. So choosing one and then going from there is going to be your best bet, is how I would prefer to have it done. I am going to convert the bottom one, the C2H6O. I'm going to convert that into the C3H4O4. I just have a feeling with the mole to mole ratio as it is that one of these is going to get in it. My limiting reactant is going to be kind of seen a little bit easier with this. I'm going to use that full calculator readout that I also had just calculated as well. And so my numbers are going to be maybe just a little bit different than yours if you did that calculation. From this, I will see that I have a value of 0.0751 moles of that is how much I need. I have 0.144 moles of that C3 3 carbon compound. So I actually have more than I need, which means my limiting reactant is going to be my 2 carbon compound here, the C2H6O. So that's my limiting reactant that I have. And so I can actually get rid of all of this other information on the top because I'm not going to need it anymore. I need to now utilize what I have from there. I'm going to take this previous calculated value and just move it up into that same area. And that was, again, that's moles of my 2 carbon, of my 3 carbon chain or that I have. I'm just going to utilize it. Sometimes there will be reference material that'll tell you to, do the convert it back into your moles of your 2 carbon base molecule. I say you already calculated into moles. The mole to mole ratio is already there. You're just doing more work. Sometimes it might be required, but sometimes it's not. And so just converting it to moles of your product that you want to have is, I think, the most logical thing to do. It's not going to get you the wrong answer. And we converted that into 5 moles of that 7 carbon molecule. that we write out here, and then utilizing the mole-to-mole ratio, H4O4, and we can see that these cancel out, and I was not doing a very good job of canceling things out like I was supposed to previously, but it happens. Now I can utilize the molar mass that I had calculated previous of my 128.17 grams per mole. You'll see that other things cancel out lovely as well. And so now I have that value to multiply across the top and then also multiply across the bottom as I do my multiplication and division, and I end up getting a value of, in theory, my value should be 16.05 grams of my of what I should calculate. What we're going to find here is that I need to now take what I've actually found in the lab is 15 grams. So if I have my 15 divided by that 16 value of 16.05, we're going to see that I end up getting about 0.93. I'm going to go 0.5, and then if I multiply that by 0.935 times 100 to give me my 93.5% yield of my product with that. So obviously much better than the Haber process on the previous problem, but this is about as long of a problem as a person can do when it comes to stoichiometry for this initial round of stoichiometry that we're going to be seeing and doing here. So hopefully this was beneficial for those of you that were gone for the choir competition today, and so we'll have more recitation off screen, and then also tomorrow in class on Thursday. So please make sure that you are prepared for that.